right, we just finished up taking a look at how do you calculate voltage for a circuit that's got resistance, and you can find out how much current is going through, because that Ohm's law says the voltage is equal to whatever the current flowing through that times the resistance. So if we look at some circuits, usually here's going to be some pictures of the way circuits work. You can either put them so that all of the elements that you're putting into the circuit are in a row, and if you can just you can just draw one path through there. That's called the series circuit. Okay. Now there's a couple things that are true when things are in a series. For instance, that the total resistance of three of these is going to be the same as if you added them up individually. So whatever those resistances were, 1 ohm, 2 ohms, 3 ohms, let's say the total of this circuit then would be 1 plus 2 plus 3. So that would have a total of 6 ohms. And what's nice about that is once you get a total resistance, then you can go back to the V equals IR, for that problem, and you can solve for it just with one calculation and then apply it up to the whole thing. What's also true, though, is voltages. If you take a bunch of batteries and hook them up in a row from the plus to the minus, plus to the minus, plus to the minus, they're additive as well. So if you put three 1.5 volt cells together by touching them head to tail, head to tail, head to tail, you're going to have 1.5 plus another is 3 volts, then you're going to have 4.5 volts. Okay, so by putting them head to tail, you're going to get bigger and bigger voltage. Now, what's true is once the current starts to flow in here, okay, what's the speed got to be? Well, there's only one pipe, so regardless of what happens through here, you're going to have the current here, here, and here. They're all going to be the same anywhere throughout that circuit. Okay, so the current is going to be the same anywhere you look. The voltages add up, and so do the resistances in series circuits. Now, there's other ways to hook these up, and that's called a parallel circuit. If you look here, there's multiple pathways for the electricity flow. What's nice about that is one of these bulbs breaks and it stops the electricity flowing here. That won't stop these from working. These still have alternate pathways. So where do they draw that? Here's a 9-volt battery, for instance. Here's your battery source. Those lines and shows the plus and the minus. The short line usually is the minus, and the long line is the plus. And the electricity going through each of these loops. Anywhere up at the top, okay, and to the bottom has the same potential drop because these are all just a wire. So the voltage from here to here is the same. So the voltage across each of these resistance, the voltage on that is the same. You could calculate how much current goes through each one of these because the V is the same for every one of them. Then you can figure out the I part because you take it times the resistance to figure each of those out. We'll do one of those in a moment. Once you know the voltage across here, like I said, you can figure out the potential. If you wanted to get a total for this whole circuit to replace these instead of having 3 in parallel to figure out what's the current through here, then what you got to do is you got to add them up, but it's not the addition, it's the inverse of these resistances. So if I take 1 over the resistance 1 over 10, plus 1 over this next one, 1 over 2, plus 1 over that last one, which is 1 over 1. So 1/10 plus 1/2 plus 1, so 1.5 plus another 10th, so it's 1.5 plus 1.1, it's 1.6. These 3 resistors in parallel are acting like a 1 over 1.6 resistance for total. So this ends up becoming 1.6 in this case. No, I don't think that's going to work. That's okay. Oh yeah, there it is. So you got 1 over 10 plus 1 over 2 plus 1 over 1. So this is 0.1 plus 0.5 plus 1. This ends up being a resistance. All those inverses end up becoming 1.6. And that's going to equal to 1 over the resistance total. So if I take 1 over that, that's going to be what the equivalent resistor would be. So 1 over 1.5, that's going to be 2/3, roughly. Okay. 3 halves, this is 1.5, 3 halves. Flip that is going to be 2/3. So let me just write that out so you can see this. The equivalent resistor then is 1 over this, which is going to be roughly 0.67. Okay. So once I get what the equivalent is, then I'd say, oh, the voltage in this case, 9 volts, is equal to the current, which is what you're looking for, times the resistance, which is 0.67. All 3 of those act like a 0.67 resistance. And that's the way you figure out what those are to calculate your current. Now, what happens if I hook a bunch of batteries in series? Well, we always said the voltage up here has got to be the voltage spread from here to here is 1. So I mean, it's the same. Sorry. So the voltage across here and here, you're not adding more to voltage. So what do you get? Well, you get the ability to pull more electrons if you need them. So if you have a bunch of things plugged in and you need more electricity coming through, having a bank of batteries is going to allow and be able to respond to delivering more energy. Where up here, if you put them all in a row, you get higher and higher voltage. You get faster and faster electrons to send through a circuit. This one, you just get more and more. You're opening up the pipe so that you can allow more things to be plugged in. Okay, so that's the way these two circuits work, and you're going to get some problems that are coming up here shortly to work on your own. Good.